Hello, and welcome back to Mechanochemistry Discussions. This seminar series is hosted by NSF-funded Center for Mechanochemical Controlled Chemistry, or CMCC. My name is Mateusz Mariański. I'm one of the center's investigators. As always, the goal of the seminar series is to bring our community together. The seminar streams live on the first Thursday of every month at 11 a.m. Eastern, although today we start a little bit later. I also would like to remind you that all of the seminars today and all previous speakers that participated in the series are available on YouTube, and I really encourage you to check them out. We also have some excellent speakers planned for upcoming months, and I hope that you will be able to join us. Before we get started, a couple of few thank yous. First of all, Dr. James Patias, the center's director, Jennifer Belzik, the center's administrative coordinator, Francesca Antillon, our outreach coordinator, and two CMCC students without whom the seminar would not happen, Ryan Kwok and Brer Hilsabek. Please do continue to follow us on YouTube channel at CMCC Mechanochemistry Discussions. And before we start, a couple of quick guidelines. First of all, this webinar is being recorded. If you have any questions, please feel free to be emailed. Please email them to cmccdiscussions@gmail.com, and we'll migrate those questions to the speaker at the end of the discussion. Second, those with the YouTube account can post questions directly to the comment sections. And finally, we reserve the right to remove the comment on the YouTube channel that do not adhere to the values of inclusion and respect for all participants. Also, we created a short survey to learn more about our viewers and what you think of the series and how we can make it better. So to participate in the survey, please scan the QR code or click the link at the end of the description of this webinar on YouTube. And without further ado, it is my pleasure to welcome today's speaker, Professor Heather Kulik, a professor of the chemical engineering and chemistry at MIT. Heather received her BE degree in chemical engineering from Cooper Union in 2004 and her PhD in material science and engineering from MIT in 2009. She completed postdocs at Lawrence Livermore at 2010 and at Stanford between 2010 and 2013, prior to returning to MIT as a faculty member in 2013 and receiving tenure in 2021. In 2024, she was promoted to the rank of full professor. Her work has been recognized by multiple awards, including Young Investigator Awards from the Office of Naval Research, DARPA, and NSF, as well as fellowships from DARPA, Sloan, and Hans Fischer, TUEM, as well as a recent award from the Presidential Early Career Award for Scientists and Engineers. It is my pleasure to welcome Professor Kulik to Mechanochemistry Discussions.
Okay, today I'll be talking about some work my group has done as a computational chemistry effort to discover novel mechanophores, primarily across transition metal complex space, but also talking about organic mechanophores. So to motivate, kind of this computational approach, we can think about all of the candidate materials that are out there in the universe. And what has happened in the past 10 years or so is that machine learning surrogate models have matured as a powerful engine to speed up and allow us to infer properties over large spaces. Zooming in here, my favorite kind of space is one consisting of many different types of transition metal complexes, which are transition metals coordinated by organic ligands. We can think about the set of transition metal complexes that have been studied experimentally before. But there are also ways we could enumerate on a computational platform new hypothetical materials that maybe have never before been studied, and we might worry about their stability or synthesizability. And then when we think about these two islands in this chemical space, one question is, if we think about all the possible materials that could ever be studied, how will you really captured all of the possibilities? And so to give you kind of one slide, high-level overview of how we think about using machine learning to accelerate discovery in transition metal chemistry, well, there's a great degree of diversity in how metals coordinate organic ligands. This in turn can change the spin state preferred by the metal center, for instance, between a low spin configuration where all the electrons are paired versus a high spin configuration. Other degrees of freedom are the metal identity and its oxidation state. So around 10 years ago now, my group developed a code called MolSimplify to automate the generation of transition metal complex structures. And this naturally led us down the path of training the first machine learning models for predicting properties of transition metal complexes. So they have, one of the things we did was we worked a lot on representation. So how do we represent the data to the model? And we trained neural networks and other lightweight machine learning models. We developed uncertainty quantification metrics, so of where should the model be trusted and where is the model untrustworthy. And using that knowledge, what you can do is something called model exploitation, where you only apply the model where it can be trusted, or you can use something called model exploration, where you look for the most uncertain but most promising points, and then you go back and acquire new data in an approach known as active learning. And our end goal with this is to develop design principles. So which parts of a molecule are most important for which parts of a certain target property. And this is a general approach that we've applied across a wide range of different properties, including redox properties, catalytic properties, and so on. But today I want to talk about specific ways we've applied this general approach to mechanochemistry. And so, as I said on my first slide, one of the challenges is how do we do this approach with awareness of what can actually be made in a lab? So I think in the first example I give you, we'll be really focusing on how do we take this approach and apply it to synthetically accessible spaces. So mechanochemistry, I like to think of as just one of the hardest areas of chemistry in terms of there's a lot of talk of enabling automation with lab automation with AI. And I think of this as an area where there's still discoveries that just take so much time and so much effort. And really where trial and error experimentation, it takes a lot of effort. So here are two examples that I really like from the center I'm a part of, the Monet Center. So this was work out of the Johnson and Craig labs that showed this very intuitive concept that if you incorporate mechanophores that selectively break their bonds into polymer networks, you actually strengthen the network properties by dissipating force. And this is a very intuitive idea, but they showed it very elegantly in this work. And then most of the time, the mechanophores I'm referring to here are usually organic molecules, but I'm very interested in transition metal complexes. So this paper from 2021 in Nature Chem from Steve Craig caught my eye. He identified that ferrocene mechanophores could have kind of unique behavior. And in particular, if you have a covalent crosslink between the top and the bottom cyclopentadienyl rings of a ferrocene, then you end up with this peeling and dissociation mechanism that's lower force than you do if you don't have this covalent crosslink. But that covalent crosslink is not compatible with what I'm showing on the left. So we're interested to know, are there ways to blend together these two observations? Noting that each of these insights required a couple of years of careful manual experiments. So we wanted to develop a computational workflow to uncover novel ferrocene mechanophores that would be compatible with polymer networks. So basically what I mean is we want this type of chemistry where the cyclopentadienyl rings are not cross-linked, but we want the mechanism of the lower force dissipation because that would lead to a stronger material in the network properties. And one of the reasons we were so drawn to this is it allows us to sidestep the challenge of synthesizability. So if you go into the Cambridge Structural Database, which is a database of all synthesized, characterized, typically with X-ray crystal diffraction, pictures of ferrocene mechanophores, there's about 15,000 metallocene complexes in the CSD. And this is a pretty big space. Once we account for the fact that we only want a single metal in the metallocene, and it turns out most of them are ferrocene, so we stuck only to iron in this case. We end up with about 5,000 unique ferrocene chemistries. And then what we're going to do is we're going to attach polymer strands to the ferrocene in our computations, and there are different ways we could attach those polymer strands. And so the total number of unique ferrocene plus polymer combinations is about 12,000. And so I'm a computational chemist by training. I run a lot of density functional theory calculations. I'm still not going to do 12,000 DFT calculations under force. So this is where machine learning comes in. So what we do is we use COGEF, which is a low-cost way to estimate the force. And we use COGEF to sample initially about 5% of the space, or about 400 ferrocene complexes. And we reached the conclusion that the experimentalists already reached, which is that doing this bridging between the cyclopentadienal rings lowers the force required to break apart the ferrocene. But we also see that there's a long tail here of unbridged cyclopentadienal rings that still have relatively low force. And so what we're going to do is we're going to train a multi-layer perceptron, so a neural network classifier, using the representation I mentioned on the second slide. And what we're going to do is we're just going to ask it to classify between this high force, low force boundary, which we're going to define at 3,500 piconewtons. And so we do a really good job of, just based on the molecular graph, that's all racks know about, is just what is the connectivity of the molecule. And it does a good job of separating the low force from the high force compounds. And so we're going to ask the classifier to tell us which points have the greatest probability of being low force. And then we're going to go back to DFT and rerun the COGEF calculations on these new samples. And so from these new candidates, you can see that this tail is greatly enriched. We have many more points now that are below this high force boundary. And, a lot of times people ask me, well, does machine learning show you anything surprising, or is everything something you could have predicted if you knew chemistry really well? And in full disclosure, I don't know chemistry really well, so I'm often easily surprised. But if you asked us beforehand, what do you expect? We expected things like strong non-covalent interactions and pi-pi stacking to mimic that covalent crosslink. And indeed, we see that as being one mechanism for lowering the force. But there's also another mechanism that I'm going to actually talk about in more detail that surprised us. But the reason that we didn't do this in a full active learning campaign, which would typically take a couple more generations, we only ran basically this after one generation, because when we then retrained the model on this new data, it only predicted about 100 new ferrocenes to be low force. And so we viewed this as having essentially exhausted the space, and then we focused in and looked at the compounds that had the lowest force here. So one of the things I mentioned is that this perceptron here on this slide, this multi-layer perceptron, is only knowing about the molecular graph. So it only knows about through bond interactions. And you can imagine that we would think that a lot of this has to do with non-covalent interactions. So we wanted to analyze other types of features we could add to a model to make it a little smarter. And one is that turned out to be really important is this dihedral angle. Basically, if the pulling points where we're pulling on the molecule is aligned, so the dihedral angle is overlapping, it's 0, that actually plays a pretty big role in determining the force of the compounds. The lowest force compounds are the cases where we're essentially enforcing peeling because the dihedral angle is 0. Another observation we make is that was surprising to us is that it's actually the steric bulk around how we pull on the polymer strand that seems to have a pretty big relationship with the more sterically crowded it is, the lower the force is to break apart ferrocene. And that's not something the experimental groups or we had any idea about, and I'll explore this a little bit more detail. But the one that we kind of expected was that non-covalent interactions would play an important role. And this is a ligand-ligand interaction we compute. We take out the iron and we compute how strong from a DFT calculation is the interaction between the two cyclopentadienal rings. And basically, if that interaction is more favorable, this number is negative. And then we see that corresponds to lower force because that stabilizes the peeling mechanism. Now, the challenge with all of these is this requires doing calculations on each of the ferrocene complexes. And the reason we didn't do these types of analyses from the get-go was because doing 12,000 of these would be computationally demanding, and training the rack classifier only requires information from the connectivity, so we didn't need any of this geometry information. It's worth noting that there were other properties that we looked at. They just didn't correlate, things like the iron partial charge, the HOMO and the LUMO of the molecule, and another set of parameters that often focus on steric bulk and shape of a catalyst, which are known as sterimol parameters. So what we did is we went back and we added the dihedral and the noncovalent interaction descriptors to see if we could make a more predictive model. So our old ROC-AUC was about 0.9. And so you can see that these new features actually improve the model slightly. We get a slightly higher AUC of 0.92. But more importantly, we can do something known as feature importance analysis. And so through this feature importance analysis, we can analyze first of all, in orange, red, green, and blue are the RACS descriptors at different levels. Is it focused on the metal? Is it focused on the ligand? Is it focused on the whole complex? Or is it focused on where the polymer attaches to the ferrocene? So you can see that the dihedral and the noncovalent interaction descriptors that give us 3D information, they actually take on about 1/3 weight in the model. So they play an important role. Then we also trained a regression model to predict the Kojève force rather than just this classification. And that model actually does a pretty good job of predicting the force required to break apart the ferrocene. And here, non-covalent interactions and dihedrals play an even larger role. And you can see otherwise, the two models have relatively similar focus in terms of how much they depend on what's going on at the attachment point versus what's going on at the metal and so on. So the not so surprising observation, we wanted to detail further and take a look at it. And so one of the things we did is we now did more careful calculations where we explicitly include the force in the calculation and then look at how the potential energy surfaces shifted. And if you've never looked at one of these plots before, this horizontal line here is where the molecule would be expected to break apart in a single molecule force spectroscopy experiment. And I'm showing the gray dashed line here is the behavior of unmodified ferrocene. And so here are two examples where the force required to break apart according to EFEI is lower. So one is this pi-pi stacking example, and the other is this example here of a non-covalent interaction with some hydroxyls and an and a carboxylate. So we can see that with ferrocene, we have essentially still near equilibrium behavior under force, even up to 1.75 nanonewtons. But when we introduce hydrogen bonding, we can see the molecule starting to deform earlier. And then we see this type of peeling mechanism with the pi-pi stacking occurring at even lower force. And we can see the significant deformation happening at 1.75 nanonewtons where this molecule is starting to break apart. So none of this is surprising. The effect of pi-pi stacking or hydrogen bonding is something the experimental groups would have probably predicted, or anyone with good chemical intuition. But the thing that surprised us much more was this role that I mentioned that steric bulk plays. And so what we observed was that we could, here I'm always showing the ref code if you see a 6-letter code. This is the accession code in the CSD. So what we identified, for example, was this NUSSEG example that has a TMS group on the cyclopentadienyl ring. And it also has this extra functional group here. So in comparison to standard ferrocene, NUSSEG significantly lowers the force required to cleave the cyclopentadienyl ring off. And this surprised us. And it also surprised the experimentalists who are much better chemists than we are. But they asked us to simplify it synthetically a little. So we said, okay, let's get rid of this extra functional group and focus just on the MTMS. And we also hypothesized that this was an electron donating effect. So basically the steric bulk helps push electron density in the transition state into the iron. So it basically stabilizes the transition state of our cleaving reaction so that the cyclopentadienyl ring will come off more easily. And we hypothesized that if we switch this to an ortho position for the TMS group, that this ortho position TMS will not donate as much electron density differentially into the iron. And as a result, it should go back to the ferrocene control. And that's indeed what we see. So ortho TMS does nothing, but meta TMS should have a big effect. And so from 5,000 initial candidates that we had, we turned to the experimentalists and we said, please try to make this meta TMS ferrocene. We think it's interesting. And so Steve Craig, and specifically his graduate student, Jaffer Vakil, synthesized both polymer strands with this MTMS ferrocene in it, which is called P2 on the next plot. And then they also synthesize polymer networks. And it's worth noting here, I'm not an experimentalist at all, but one of the challenges we encountered with this project was that even if a molecule was already in the CSD and had already been synthesized, we also had to think about compatibility with polymer strands and polymer networks, which introduces new synthetic complexity beyond just, oh, can I make this ferrocene? So this was by no means an easy task. The computations were still much, much faster than just synthesizing this one molecule. So we see the expected behavior in comparison to ferrocene in the single molecule force spectroscopy single strand experiment. We see that our MTMS ferrocene is more reactive, so it breaks apart more quickly. And then this is a TER experiment, so covalent control. So this is in polyacrylamide gels. In comparison to covalent control, the ferrocene can be strained 50% longer, and then our MTMS ferrocene can be strained twice as far as that. So we achieved over fourfold increase in network toughness just from our molecular scale predictions. But I think my favorite thing about this is the fact that this is a phenomenon you can see with your eye. This is the first time in my career that I've made a computational scale prediction just with molecules that I've been able to show is something that we can see with the human eye. And so we're just seeing the results of this experiment visually. So the control broke first, ferrocene is going to break next, and then our designed polymer with MTMS ferrocene tears last. So that's all I have to say about this, but just to reiterate before I move on to my next topic, that we were able to use machine learning to uncover a novel design principle for how to toughen polymer networks. We came up with one candidate from over 5,000 possible candidates, and it was not one that followed chemical intuition or expected behavior, even though we uncovered many designs that sort of followed what you would have expected based on chemical intuition. And our goal now is just to generalize this type of approach. Another thing that we concluded from this that's useful to note is that there's many opportunities to repurpose materials. So there are many, even though we would like to go and discover totally new molecules, there are many molecules that have been made before but have never been used for a specific application. And I think this repurposing is a great way to sidestep the challenges of whether or not a computationally designed material is synthesizable. So now I'm going to switch gears a little and tell you briefly about something we've done also working with experimental data, but more in the organic space. And this is a collaboration we did with Jeff Moore and Steve Craig. And what we wanted to do is note that there's been an increasing amount of data out there at the single molecule force spectroscopy level of knowing how different mechanophores are reactive. And sometimes those reactions are a little bit surprising. So for instance, if you take these types of mechanophores and you make the acyl endo or trans, or you make the alkyl endo or exo, you get different cleavage patterns, and these are not predicted correctly by COGEF. So COGEF can't correctly order, for instance, that this one on the right, I don't expect you to remember the terminology at all. The one on the right is the most reactive, and the one number 2 is the least reactive. And in fact, there's lots of these out there. There's the lateranes, there's all sorts of gem difluoro, gem dichloro, cyclopropanes. There's all sorts of ones where there are different levels of reactivity out there. And so we gathered all this data, any case where there's a CC bond, to try to build a model to explain how can you predict, without having to resort to COGEF, how can you predict the experimental CC bond cleavage? And one of the ways to conceptualize this is that we first have some initial force that activates the bond. So we can know a lot about this from just near equilibrium properties. And then we have the transition state where the bond's about to cleave until we get the final intermediate. And so we'd like to be able to train a model that can predict how subtle changes in geometry or in local chemistry alter the cleavage force. And so here are EFEI simulations on these same 4 mechanophores, and EFEI does a good job of actually capturing the relative reactivity. So it does a good job. It predicts that the acyl trans is the least reactive, and it's less reactive than acyl endo, and that alkyl endo is less reactive than alkyl exo. But we don't want to do EFEI simulations all the time because they're time consuming. And so what we hypothesize is that the reactivity should be a function of how force responsive the bonds are, as well as what would the reaction energy be under force. And to be honest, this is a nice conceptual picture, but when we were first trying this, we were just trying to find some descriptors and see what could fit the data kind of thing. And these were the 2 that we ended up on. So we're going to define something called the K effective, and that's basically how does the bond length change of the CC bond when applying different external force. And this is a little bit easier than doing full EFEI calculations because we're just doing a couple of optimizations under force to fit this line. So here I'm showing about 20 data points, but we've shown that you can do this with about 3 data points. And then in addition, you can do the force-free optimization to get the reaction energy. So that's just 2 calculations, the reactants and the products. And the way to conceptualize this now that we have this nice descriptor for CC bonds is that for reactions with the same driving force, we can think of this as the energy is the energy we have to impart to the system is the area under the curve of these triangles. And if the K effective is higher, then the distance between the activated state and the transition state is slightly smaller, but the peak of the restoring force is higher. Whereas when we have a higher energy required to impart for the reaction energy, but the same effective force, then we have even more work to do because the driving force has to be higher. And so does the model work? Well, the answer is for the most part, yes. So here I'm showing these are experimental forces. And then these are the K effective and delta E and the resulting predicted forces. And so most of the time we're able through this fitting approach to get within, say, 0.1 or 0.2 nanonewtons of the experimentally reported force. There are exceptions where we do particularly poorly. So most of the cases we do kind of poorly on are the cyclobutane mechanophores, though there are exceptions. So here's an example of one with this highly strained case we do poorly on, but you can see most of them were within about 0.1 nanonewtons. And this is what the data looks like in practice. This is our expression. So it's a weight of the force-free reaction energy in this K effective value, and we get an R squared of about 0.88. And so you can see there's some points that lie off the line, but many points that are consistent. And there are tutorials on how to use this if you're not a computational chemist who normally does these calculations. There's tutorials on how to use this to estimate the force, say, to pre-screen other mechanophores with CC bond cleavage. So that's all I'm going to talk about here, except to say that our current work in the group is focused on generalizing to other classes of mechanophores. This was only CC bonds, so you can think about other types of reactions that occur, both heterolytic bond cleavage, as well as the ones that didn't fit well in this set. So we're working on how do we generalize this and what other pieces do we need. So now I'm going to jump back for the last part of my talk to transition metal complexes. And we were interested in controlling other behavior of mechanophores. And this was work done by Xiao Huang, a fifth-year chemistry PhD student in my lab. And we were interested in understanding, could we impart force as a way to control other properties of transition metal complexes? And so we were interested in designing mechanophores that would change their spin state under force. And so what we did is we searched in the Cambridge Structural Database for bis tridentate complexes that would be compatible as mechanophores. And we looked specifically for iron and cobalt complexes. And we ended up with basically about 400 of these to screen after you account for polymer attachment points. And it turned out this was actually ridiculously easy to do. So most low spin mechanophores become high spin under under force very easily at relatively low force thresholds for both iron and cobalt mechanophores. Because pulling on those bonds very intuitively favors the high spin state, which has a more anti-bonding character than the low spin state. And so, well, how could we predict this going forward if something would be a force responsive spin crossover mechanophore? Well, the force-free spin splitting tells us pretty well. So for instance, the lower force of mechanophores, the lower the force-free spin splitting is, the more likely it is that something will require relatively low force. This is the force in nanonewtons. So for instance, if the spin splitting is only 3.5 kilocalories per mole, then the force required to trigger that spin transition is only about 0 to 0.5 nanonewtons. But there's also an interesting bifurcation of the data. Many of the complexes stay intact until very high forces, so only a few of them tend to transition at below 3 nanonewton force into a new structure. So they're still intact, but they're changing their spin state. But what we also found was an interesting class where we showed that they sheared to form instead, they started as octahedral TMCs and they sheared instead to form square planar structures. And so this really interested us. And we're interested to know if this was a general phenomenon of octahedral mechanophores. And so this time we went back and we looked at them in the context of copper, which favors both 6- and 4-fold coordination more evenly than mid-row transition metals. So here we looked for tridentate FAC symmetric complexes, and we looked specifically for candidates that we could combine with copper, and we ended up with a space of, again, about 750 complexes. And we found that indeed many of these copper complexes convert to square planar structures at low force. And so there's a slight difference here in whether we're pulling on this in the beta position versus the alpha position. And we use that nomenclature because it won't be meta versus ortho if it's five-membered rings. And so some of these have 5-membered rings, some of these have 6-membered rings, but we basically see that we see this transition to square planar occurring at relatively modest force in many of these copper complexes. And we can look more closely at what happens. And we see that we have this interesting effect that the bonds that aren't cleaving, they actually shorten and they stabilize the square planar structure as the one that does cleave gets longer. And this happens even before we reach the critical force. And we also could screen for whether or not these are thermodynamically stable mechanophores. So basically, how much energy is it required in the force-free application to go from octahedral to square planar? And generally what we see is that we can push up and identify numerous complexes that don't have much thermodynamic driving force. They actually have quite significant penalty to form square planar without force applied, but they will still cleave when applied force is applied. And in particular, it's the alpha type mechanophores are much more reactive, so it's harder to reach, like, say, a very high thermodynamic stability that's equivalent to organic mechanophores for these very reactive ones. But we can have sort of the sweet spot where we have complexes that will break apart at relatively modest forces, but still have pretty high thermodynamic stability. That's what I'm showing there. So I'm just going to finish up with one quick additional mention that I think is of potential interest. It's not quite in the space of mechanochemistry, but it's mechanochemistry adjacent. And that's that everything I've been showing here, we assume we know exactly how a ligand binds to a metal. But there's lots of cases where you have a new ligand and you're not sure where it binds to a metal. And the first time we did this, we required that the ligands only bind the metal in one unique way. And we searched the Cambridge Structural Database for these examples. So I'm calling this non-hemilabile. And so there's about 75,000 ligands that we can work with, or I guess in practice about 70,000. And most of these are bidentate. And I'm going to use the phrase bidentate to refer to anything that binds with 2 coordinating sites. So that's really, I'm going to call this coordination number, although denticity and hapticity are more complex concepts, and those can be mapped back to what I'm going to show. And so most of these in the CSD are nitrogen coordinating. There's a very small minority, for instance, of silicon coordinating. And we're doing this in a metal agnostic way, and we have information from many different metals. And the reason for that is that there's just not enough data for metal-specific coordination. And so what we did was we had enough data to train graph neural networks to predict coordination number. And when the model is wrong, it's usually wrong by just one. It predicts a bidentate as a tridentate or vice versa, and so on. So here's an example where the model is wrong. It predicts 2 coordinating atoms, or it predicts 1 coordinating atom, but 2 is the correct answer. Here is a pentadentate ligand, but the model only predicts 4 of these atoms to be coordinating. But it does really well in a lot of the, especially for bidentate prediction. Its accuracy is 88%, its AUC is 98%. And more importantly, to enable end-to-end structure generation, we trained our model to predict coordinating atoms. And this is easy to get a really high accuracy. You can get a 98% accuracy because the answer is no most of the time, much more common than it is yes. So we instead looked at other metrics such as positive accuracy, negative accuracy, or balanced accuracy, and we defined a new metric we call molecular accuracy, which we achieved about 85%, which is, does the model predict correctly every atom in a ligand as either a yes or no? And that's a much more stringent case. So here's an example of the model predicting the coordinating atoms. It predicts these 2 atoms correctly, and this one incorrectly. The correct answer should have been this atom. So even the wrong answers are very plausible. And you could ask, well, did we have to go through the trouble? Could we have just counted up the heteroatoms and assume any heteroatom is coordinating? That would have gotten us a 22% accuracy. So the model does a great job of doing things like predicting the difference between atoms that coordinate and atoms that don't coordinate. It also can predict high density ligands. It can predict hapticity. So I would call this a 6-coordinate ligand, but it correctly captures that this is a haptic interaction. And it can also detect that silicon is the coordinating atom here, even though there are much more common coordinating atoms nearby, like this phosphorus. And since we have both a coordination number and a coordinating atoms model, we can actually use them synergistically to enforce chemical consistency. So the model predicts very confidently, confidence would be a number close to 1 here, that this is a bidentate molecule. But our coordinating atoms model is only confident about this phosphorus, and then it's fairly uncertain. It predicts that the sulfur is just weakly uncoordinating. So we override the coordinating atoms model with our coordinating number model, and we instead assign both of these atoms to be coordinating, and that is actually the correct answer. But I want to come back just as my very last point is that thousands of ligands are hemilabile, and we actually defined 4 classes of hemilability. Class 1 is the most intuitive, that you can make or break a bond between 2 coordinating modes. Class 2 would be you have a change in coordination number, but also in coordinating atoms. Class 3 would be the number of coordinating atoms stays the same, but there's some sort of mismatch between which atoms are coordinating. And then class 4 would be the coordination number stays the same, but there's no overlap. So these are all different types of hemilability. Class 1 is the most common, but we can all think of examples of the other classes. And so we previously predicted only class 1 hemilability in this first work published in 2023. And the main thing that we accomplished there was it's really hard to have negative examples of hemilability that are robust. Just because something hasn't been observed to hemilabile in the CSD doesn't mean it isn't hemilabile. And we also uncovered unexpected design rules by doing feature importance. So we developed a smarter way called semi-supervised learning to identify which are the most confidently non-hemilabile ligands. And when we trained the model, we observed that a lot of the hemilability is dictated by things very far away from the metal, not the coordinating atoms. So we went back and did this on all 4 classes and trained a GNN. And what we did was we took our pre-trained model that predicts coordination number and we fine-tuned it with coordinating atom uncertainties. The idea is that coordinating atoms will be uncertain for hemilabile ligands, both because 2 answers are both correct and because they were not seen in the training of the original model. And the fine-tuning helps improve accuracy quite a bit. It's challenging to achieve the accuracy of the smaller model that had a smaller data set for a few reasons I won't get into details of, but you can see that this is The true model thought, the true label is non-hemilabile. The original model thought this was hemilabile, but our fine-tuned prediction knows that it's not. And this is an example where the true case is that this is a hemilabile ligand, and the original model thought it wasn't, and now our fine-tuned model thinks it is. It doesn't fix everything. This molecule looks a lot like terpene to the model. And so the fine-tuned model is more, this is not hemilabile because of these carbonyls. The model is less confident after fine-tuning, but it's still wrong. So it's not perfect, but it improves a lot in the right direction. And so now we have an ensemble approach to predicting alternate conformations. What the model takes in is smiles, and it outputs a 3D structure with MolSimplify. We recently published a newer paper on our MolSimplify code with a number of improvements. And so it can predict the ranked coordination numbers of different types of coordinations. It'll enumerate those coordinations with the hemilabile model. And we wanted to compare, and basically what this graph is showing is that for things that we know experimentally are hemilabile, the ones that we predict to be hemilabile with our model are pretty consistent. And the ones our model predicts to be non-hemilabile are also pretty consistent. So this supports the idea that the model is predicting plausible modes of different hemilabile coordination. And I think that this could be used in concert with mechanophore discovery to identify labile mechanophores that can adopt different coordination modes in response to force. So I went a little long, but I'd like to finish by concluding and saying that main thing I wanted to tell you about was our work on ferrocene mechanophores, how we got from computational designs to 4 times tougher materials. I also introduced our model for CC mechanophore reactivity. And finally, some of the high throughput screening efforts we've developed to uncover transition metal mechanophores. I'd just like to finish by acknowledging the students who did the work. The work on transition metal mechanophore screening was done by Xia Huang. The first work I told you about was done by Ilya Kevlishvili, who's now at Baylor in his own tenure track position. Heechul Zhang is continuing the CC TMBA model. And then I told you about some of Jacob Tony's work at the end. And thank you for your attention.
Thank you very much, Professor Kulik, for your interesting talk. We have a couple of questions from the audience, if you could answer us. So the first question is about the first project that you presented. And at the beginning, you mentioned that you use COGEP to sample, I think, 5% of the conformational space. So the first question is, how do you select this 5% of the conformational space, meaning the direction of the deformation? And then the second question is somehow similar, is that how do you select the force that you use in the FA optimizations later?
Yeah, so for the 5% of the space, we cluster, and then we pick the most representative structure. So we try to pick something that diversely represents the full 12,000 compound space. So you take the full space and you use something like RACS, and RACS tells you how similar or dissimilar the different molecules are to each other, and you try to take a 5% representative space that basically everything is a little bit different from each other. So you try to get good coverage of the space. Then for the EFEI that we're showing here, we usually do it in half nanonewton increments up until we see a cleavage event occurring. I think I showed a few different EFEI examples, but here you can see we're doing it in these half nanonewton increments. Same thing here, it's just different half newton increments. And the reason for that is just EFEI calculations are expensive enough that if you do them in many, many increments, that takes a lot of time. Now, an exception to that is when we were just trying to show this relationship between K effective and the bond length. You can see here we're doing much, much finer increments of about, I think, 0.05 nanonewton. But normally for high throughput screening, we want to do it on the scale of half nanonewton because anything more is just too computationally demanding, and usually you see this linear behavior. If we didn't see the linear behavior, then we might do more points. I think that answered both of the questions.
And the direction of the force that you use here represents the peeling that you have as your model.
Yeah, so this is showing, for example, the ethyls. So the ethyl groups are what are used. The endpoint of the ethyl groups are used for the pulling apart. And this is showing different snapshots of how the geometry is changing with these different forces. So you can see here the dihedrals, the pulling points were aligned more here in this example than in this example, than they're at 180 degrees.
So the next question is somehow related, but from the perspective of experimentalists. And the question is, how do experimentalists apply forces to these molecular systems? And how do they know which bonds feel the force?
So they don't. Computation, I believe computation is usually used for that, although there's probably something interesting that could be done there, at least as far as I know. So what I was showing here, for example, is single molecule force spectroscopy, where we do have, we have an AFM tip and we have a polymer strand, and we're basically pulling on the polymer strand. And there's reporters that tell you when the polymer strand has broken. Sorry, that's not showing this experiment. But it's, only a few labs in the world have this expertise and have this ability to do this well. So it's much more common to do sonication experiments where a bubble collapse helps tear apart a long polymer strand, and then our connection to knowing for sure which bond breaks is even more indirect. And I'd say that is why these types of computations are quite widely used, because it's important to know which bond breaks, what additional bond breakage events might occur after that bond breaks. Is it a heterolytic or homolytic reaction? Those types of things I think are easiest to tell from computation. There are almost certainly ways to tell from experiments, but I'm not an experimentalist. But I would say it's mostly indirect, or say detecting a radical by capturing that radical by its reaction with something else, for example. So there are ways to detect, but the most clean comparison between the computation and experiment, I would say, is the single molecule force spectroscopy. These more macro scale things, or the sonication, are a little bit more indirect versus computation. But in general, we've found that the computation is a good, provides this additional insight into what bond breaking is occurring.
So we have two more questions, again, one computational, one experimental related to that. So the computational question is that, could you comment on your confidence on the density functional approximations to predict the high spin, low spin gaps in the D-transition metals? And if you could share a little bit about the recipes that you use for that. Because I think that is...
Yeah. So iron, so a whole different life. I have like a whole different, I could have given a whole talk about whether or not I trust density functional theory for high spin, low spin gaps. That's something that we've worked on very extensively. But the short answer is that for a narrow range of ligand fields, and for a fixed metal in oxidation state, or what's, I should back up. Hartree-Fock exchange is probably the most significant tunable knob in your density functional approximation to determine what the balance is of high spin and low spin states. And that selection of Hartree-Fock exchange is highly metal oxidation state and ligand dependent. But iron 2 systems, for example, have been studied a lot. And it's known that a fraction of about 15% exchange, which we calibrated, is a good fraction for determining this high spin, low spin balance in iron 2. And so we pre-calibrated our choice of Hartree-Fock exchange so that the model would be predictive. And we also have a separate paper where we look at experimental spin crossover complexes that are known experimentally, and which functionals give the best performance and things like that. So I'd say we're pretty confident on iron 2. We're maybe a little less confident on cobalt too, but yeah, I could go on forever about that. That's definitely something that we've spent a lot of time thinking about, but I didn't mention it here. This was calibrated and was it basically something that was first popularized as B3-lip star, because it does a good job of predicting this population.
And a somehow related question is that now, if you could use force to change the spin states of the of the metals, can you imagine engaging these metals in acting as a catalyst to create some form of chemistry now based on that?
Yeah, that's actually what we were hoping more with these conformation switching things, or this is my hope. My hope is that you I mean, you could think about it in catalysis with just preserving the octahedral coordination, but I'd worry about not having an open site for catalysis. But the idea here was if we unmask basically an active site and then the square planar species is reactive, but the octahedral is not, we can make the square planar do catalysis. And what I'd love to make it do is probably something very simple that we could screen for easily, like hydrogen evolution reaction or something super easy that would happen at a square planar, in this case, copper site. But yeah, that's the idea, is that some of this transitioning. Now I have a postdoc who's also looking at like the interplay between changing spin state and changing redox. So can we use force to change the redox potential of these? And that might also be kind of an avenue to get us closer to catalysis. But that's our long-term interest for sure.
That's very interesting. Okay, so these are all questions that we had. So once again, thank you very much, Professor Kulik, for your very interesting talk. And thank you very much for listening.
Thank you.
Thank you, Professor Kulik, for outstanding presentation, and thank you very much for joining us. Just to remind you all of the previous seminar speakers are always available to watch on any time on YouTube. We also have some great speakers. Change of slides. We also would like to remind you that we would like to hear back from the community, especially how we could improve the seminar series. And I really encourage you to scan the QR code or click the link in the description of the video and provide feedback to us. And with that, I would like to also remind you that we have some excellent seminar speakers planned in the upcoming months, and I hope that you will be able to join us. Thank you very much again.